Hello everyone, today I'm going to give a short talk about Gridfins, but first of all, I'd like to make a short announcement. The spacewalk that was scheduled for today has been pushed back to next week. Meanwhile, tomorrow's Falcon 9 launch still stands, and the Falcon Heavy launch on February 6th has now also a time to its date, which is around 18 o'clock GMT, opening in about 3 hour launch window. Now, I haven't made too many videos lately since I am a little bit busy, but I'll try to pick that up again until the Falcon Heavy launch, since I do want to comment on that in more detail. However, today I'm going to talk about one detail that is somewhat essential to SpaceX in general, including the Falcon Heavy, although it is of course nothing new, and in fact it has been around before SpaceX. Gridfins were not invented by SpaceX. The idea of a gridfin was around since the 50s, and several space pioneers have worked on the idea. It has been come up with in parallel in the USA and in Russia. And in fact, Yuri Gagarin himself, the first human to ever go to space, who also had a bit of an engineering background, did also work on that concept himself in theory. And you can see that many early and later Russian rockets, which is somewhat intertwined since the newest Russian rockets, the current modernized Soyuz versions which carry humans to the ISS, are essentially vastly overhauled and modernized versions of the R-7 rockets, the first Russian rockets to launch a satellite into space. So they did take over many design elements. Doesn't use grid fins usually. It has grid fins. The grid fins are used for the launch escape system in case something goes wrong. So if a Soyuz rocket ever explodes and the launch escape system kicks in and saves the astronauts' lives by pulling them away from the rocket rapidly and letting them descend on a chute, this launch escape system will be controlled by grid fins. And this is where you may first have seen the appearance of grid fins, or lattice fins as they're also called, with their quite unique look, looking a bit like, well, a grid, which is something you don't see too often in aerodynamics. And of course, they are often misconceived as air brakes, which, I mean, they do have some braking effects, and this is one part of their purpose sometimes, but it's not really mainly what they do. They really replace normal fins and have a few advantages and disadvantages, which somewhat explain their use mostly in the Falcon 9 landing stage, in the Soyuz launch escape system, and sadly quite frequently in guided bombs and small missiles. Now, the grid fin principle is pretty simple. You have a lot of short, small fins or wing segments that can be more or less aerodynamically sophisticated. Usually they are actually just flat, although there are a few designs with actual supersonic wing profiles. But the actual profile of the fins is usually just a flat rectangle-like thing. And these are arranged in this sort of grid, and so they work together like an extreme biplane or multiplane in several directions, and they can provide anything a normal fin can. They can provide stability, they can provide control if you move them, and they can provide some air braking if you are going very fast and your spacecraft is otherwise relatively small. Now, their main disadvantage is, of course, that they are far from aerodynamically optimal or perfect for their job, and they do create a lot of drag, especially in transonic flight. They are relatively efficient in subsonic or hypersonic flight. At hypersonic flight, they actually get really good, but at transonic flight, just before breaking the sound barrier or just above the speed of sound, or, of course, hypothetically at precisely the speed of sound, though that is obviously a very, very short moment, they perform very bad. They don't create that much lift and control, and they create a lot more drag, which can be quite easily visualized. It does work a bit like a biplane after all. And what essentially happens is, since you have these multiple fins, these multiple airfoils arranged close to each other, the shockwave from each of them essentially collides with the shockwave from the others. And at transonic speed, what that means is that you essentially get one giant shockwave at the front, at the inlet of the grid fin, basically, and most of the air is just shoved around the grid fin, and it behaves Not exactly, but a little bit like it was just a square block of metal rather than a sophisticated grid fin. Whereas at subsonic speed, of course, the air just flows through and it's not perfectly optimal, but it works. And at hypersonic speed or very high supersonic speed, you've all seen how Mach cones behave at higher speeds. They get pointier because the air is sucked backward quicker, while the shockwave still expands at the same speed. And so at high supersonic speed, the shockwave actually just barely leaves the axis it was created on. It barely expands at all, and so these shockwaves only really collide in the very corners of the grid sectors, and so it's relatively efficient again. In fact, if you run it through quite complicated computer models, you can find out that at hypersonic speeds they actually turn out surprisingly great. Now, one big advantage of the grid fin is of course that it is easily stowable. It can be folded in rather simply. This could also be done with a normal fin, but by far not as easily. It's also really good as a control surface for high-speed aircraft that aren't under continuous power, since they don't need much force to turn. Since the fins are relatively short, there's actually relatively little torque on a grid fin compared to a normal fin. If you imagine a normal fin being attached at its leading edge, and you want to turn it and it creates lift or control force, then you will have to fight against that force to turn that fin. On the other hand, if you mount it at its rear edge, then you'll have the opposite. It will want to turn 180 degree and you have to hold it back. And if you mount it in the middle, you can kind of counter that, but you'll never be perfectly precise in this. And so especially if it goes from supersonic to subsonic, you'll always have some forces to work on. A grid fin does still have these problems, but vastly reduced because the fin itself is shorter along the length of the vehicle, so the same force creates much less torque. As for SpaceX, they actually use relatively advanced grid fins. These are somewhat weirdly shaped, and you actually rarely see that, so they are often misconceived as mere rectangles, which is a somewhat valid approximation if you just do a really rough estimate. I've done simulations like that before, but the actual grid fin, it is mostly smooth on the upper side. It is of course overall rounded to fit along the rounding of the Falcon 9 fuselage itself as it is folded in, but the upper side is relatively smooth. That is when the Falcon 9 is descending, the rear side. And when the grid fin is folded in, that is also the outer side. It's also the side you see from the outside. It's also the side that is filmed by the onboard camera of the Falcon 9. So it is really the side that is most often seen. And so the conception has been spread that the grid fin is completely smooth. But on the underside, it's actually somewhat of a waved pattern. And this helps with the supersonic effects of a grid fin. It does have a few other advantages as well, but mostly it is there in order to smoothen out the shock wave that comes from the leading edge of the grid fin. Now, since it has this kind of wavy pattern, what essentially happens is that you get a shock wave on different points of length along the grid fin airfoil depth, and so the shock wave is somewhat smoothened out. There is not one sharp shock wave at that beginning, but rather that beginning is waved out, so it's at several points, and so that shock wave starts at different lengths at different points and thus is basically distributed, and there's not as much shock from the shock waves hitting each other or reflecting each other, which makes the Falcon 9's ride through the sound barrier on its way down just a tiny bit smoother compared to that of some bombs. Which is somewhat important since the Falcon 9 is pretty huge and the grid fins are under quite a bit of mechanical stress and they're trying to build them as lightweight as possible, so any reduction in stress on those grid fins is a win for the overall rocket design. Now, the last thing I'll address is just a little detail on the Falcon Heavy that many people have spotted, that the grid fins are of different colors. If you look at the core booster, the grid fins are white. If you look at the left or right booster, they are dark. And that is simply because on the Falcon Heavy, these boosters will re-enter at different trajectories and different speeds. Since the left and right booster will jettison and fly back to Cape Canaveral and land there, they will re-enter at a much lower velocity but much steeper, whereas the center core will fly on and land on a drone ship in the Atlantic after accelerating to an incredible speed. Since it is the Falcon Heavy, it does boost that center stage, so it re-enters at higher speed than any Falcon 9 stage before. It does, however, re-enter a lot flatter, since it is basically close to an orbit trajectory, and I will probably later on make a video more into detail on re-entry optimization, heat shield optimization, thermodynamics in this specific application, high speed heating, low speed heating, rapid heating from dense air, less dense air, and so on. But the optimization essentially says that the grid fins from the cars that re-enter steeply but slowly should be dark, while the grid fins of the car that re-enters quickly and more shallow should be white in color, so they have been painted. In the end, of course, on the landed stage, we can expect that most of that paint will probably have been damaged to the point where the grid fin is pretty much bare titanium again. So this was my short introduction to the physics of Gridfins. If you have any further questions about spaceflight, the Falcon Heavy, or the physics behind spaceflight and aviation, I'm always open for any questions and I'll see if I can find the time to answer them. And as always, thanks for watching.